Right, this is Honors Geometry sections 11.1 to 11.3, and this is video part 1. We'll do a few parts of this, and to begin with, I'll just be introducing a lot of the general formulas that we'll be using, starting with some ones that I'm sure you're already familiar with. The standard area for a triangle is 1/2 base times height. In other words, we have a triangle. If I know this length, I'll call it my base, and then the height is the perpendicular height to it. And so 1/2 times the base times the height would give us the area for that. Another way to find the area of a triangle you're probably not familiar with is called Hero's formula or Haran's formula. To begin with, if you have all three sides of a triangle, we're going to add them together and divide by 2, and that's going to solve for S. S stands for the semi-perimeter. It's half of the perimeter. Once you have this value, then we're going to evaluate it using this formula. The square root of S times S minus A times S minus B times S minus C. This is a nice formula to have when you know side, side, side in a triangle. Next, area of a rectangle is base times height. Area of a square is side squared. The area of a parallelogram is also going to be base times height. If I look at a parallelogram and deconstruct it, I could take this rectangle, slide it over to the other side, and make just one big rectangle, and it would just be the base times the perpendicular height. In fact, anything in the parallelogram family is going to have base times perpendicular height. Trapezoid is also essentially going to have base times height. We're not just going to use the top base or the bottom base, though. We're going to take the average of the bases. And if you think about that, the average of the bases, in other words, base 1 plus base 2 divided by 2 is the length of this mid-segment. So the mid-segment times the height would be the area of the entire trapezoid. So I started off with a trapezoid that looked kind of bad like this. And then here is the height of the entire thing and deconstructed it. This mid-segment times the height of the entire trapezoid would give us the area. If you think about taking this small little trapezoid at the top, once it's been split, rotating it over to here, and bringing it over to here, then you have this new trapezoid that has half of the height as the original, and the entire base is base 2, base 1, and we have this parallelogram. Base 1 plus base 2 times the height. Since a rhombus is a type of parallelogram, we can say the area is base times height, or recall that one of the properties of a rhombus is that the diagonals are perpendicular to each other. So I'll draw both of them in there. And this length, we'll say, is 1/2 of D1. And then this length, we'll say, is 1/2 of D2. So to find the area for this one triangle, we would do 1/2 of 1/2 D1 times 1/2 D2. Right? It's 1/2 base times height to get the area of that one triangle. But there's 4 of those congruent triangles that make up the entire rhombus. So then we're going to have to multiply this by 4. 1/2 times 1/2 times 1/2 is 1/8. 1/8 times the 4 out front would be 4/8. In other words, it simplifies down to the 1/2 D1 times D2. So this is another option to find the area of a rhombus. Like the rhombus, we can find the area of a kite using that same formula. The interesting thing about the kite is even though it's not in the parallelogram family, so it's not a rhombus, it does have perpendicular diagonals just like the rhombus. So the idea is if this length is D1 and this length is D2, then the area of this entire kite could be found by doing 1/2 times diagonal 1 times diagonal 2. Other ways to find the area of the kite would be to use what you know about a kite. For instance, depending on what you have, maybe you want to find the area of the small little triangle or this bigger triangle up here, or the entire left half and then double it. Lots of ways you could do it, but if you have these diagonals, this is a quick way to find the area. At this point, I would pause in your notes and try some of the next problems, and I'll scroll down here in a moment so you can see my work for those and see those answers. In the first example, you had a right triangle. If you use Pythagorean theorem, this length is 12. Then the area of the triangle is 1/2 times 5 times 12, which gives you 30. The next one is a square. If you use Pythagorean theorem or special right triangles, you would get that each of these sides is equal to 4 square root of 2. And then if you took sides squared, that would give you the area. Another way you could do this one is recognize that a square is a type of rhombus. And in a square, the two diagonals are equal to each other. So you could do 1/2 times diagonal 1 times diagonal 2. That would be 1/2 times 8, which is also 32. And the next one, we have an isosceles trapezoid. So one of the skills we want to employ here is to draw in 2 auxiliary segments. It creates a nice rectangle in the middle where opposite sides are both equal to 10. And then on this left-hand side, we know we have lengths of 2 and 5 because the 14 is 10 taken away from it, and it's split evenly between those two sides. Using Pythagorean theorem, we get that the height is square root of 21. Then the area of the entire trapezoid is the average of the bases, 10 plus 14 divided by 2, times the height of square root of 21. Next example, we have a kite. We have a length of 8, a 6, and a 10. So there's a lot going on in this one. This diagonal going from left to right is being bisected by the vertical diagonal. So now this length is 4. Using Pythagorean theorem, this length is square root of 20 or 2 root 5. Using Pythagorean theorem on the bottom, this length is square root of 84 or 2 root 21. So then I went to the kite formula for area. 1/2 times diagonal 1, which was 8, times diagonal 2, which is 2 root 5 plus 2 root 21. 1/2 times 8 is 4. And then distribute the 4 to both of those values, and here is a nice exact answer for that one. The next example that you see is a rhombus where you have lengths of 14, 14, and 12. So I took this grade triangle, dropped it in altitude. I took the grade triangle, used Pythagorean theorem. This length is 4 root 10. And then what I decided to do is let's find the area of this one triangle. Color here to green. So the area of that green triangle is 1/2 times base of 12 times the height of 4 root 10. But we have to double that because there's an equal triangle down here. So then the 2 times the 1/2 cancel each other out. We multiply to 48 root 10. Definitely not the only way to do it, but that's one way we could get that area. This next example is the first time that we're using Hero's formula. We have all 3 sides, so if you add up all 3 of those sides together, it comes out to 28. 28 divided by 2 is 14. So the semi-perimeter for this one is equal to 14. For the area then, it's 14 times 14 minus 12 times 14 minus 7 times 14 minus 9. So we have all these values. And if we could multiply it out to get one really big number, or I can start breaking it down into ways that I think are going to be beneficial. In other words, the 14 I can split into 7 times 2. 7 times 7 is 49, so we can take a 7 to the outside. 2 times 2 is 4. The square root of 4 is 2, so take a 2 to the outside. And only the 5 stays on the inside, so it breaks down to 14 root 5. So there's some algebra to simplify it. Other ways you could do that. But here's a nice exact answer for that one. This one may take you a little bit longer, but we have 4 vertices of a quadrilateral on a graph. And we could draw in either diagonal. I drew in diagonal BD, although diagonal AC could have been drawn in as well. And we're going to use Hero's formula on this one. So you can use distance formula to find the lengths of all the sides in this yellow triangle. I have that. And then I stored those values as the square roots in my calculator. Find the semi-perimeter, store that as x. And you could store it as any letter. S is a nice one, but X is the easiest because we're going to bring it up quite a few times once we plug it into the Hero's formula. So the area of this yellow triangle is the square root of that x times x minus 8 times x minus a times x minus b. And it comes out the exact value of 20, which is pretty interesting considering we have all these square roots in there and they get really jumbled up, but the area of this shape is exactly 20. And then for the green triangle below, you're going to do the same thing. I would store the second value as A, the third value as B, and then if you scroll back up in your calculator, you can use this exact same line of code again, so you don't have to type it again, and it comes out that this bottom area is 20 also. It doesn't always happen that it's split evenly like that, but both of those have an area of 20, so if you add them together, you get an area of 40, and this is one way you can find the area of a quadrilateral when it's on a graph. Not too bad. But that brings us to this next example that is a concave pentagon. Now to find the area of this entire thing, some options would be to draw in a diagonal like this, which gives us one triangle, and then I can draw in another diagonal, which gives us a second and a third triangle, find all three of those areas and we've got it, but that's going to take quite a bit longer. So what we're going to do is look at what's called the Shoelace algorithm. Here are all the coordinates for the pentagon, and I put them in order going around the perimeter. I went clockwise. You can see how I color-coded them to put in there, although you could have gone counterclockwise. And you could start at any point you want to, but I'm putting them into this matrix array. Out front, I put the number 1/2, although sometimes it's going to be -1/2, depending on what order we put them in there, and we'll see that in a second. And next thing we do is we multiply. 3 times 11 is 33. 5 times 8 is 40. 12 times 5 is 60. 9 times 6 is 54. And then 4 times 5 is 20. So I have all of those going in one direction. I'll change colors minus, now here's the shoelace part going in the other direction. 4 times 5 is 20. 11 times 12 is 132. 8 times 9 is 72. 5 times 5 is 25. And the last one, 3 times 6 is 18. So we go in one direction, we add all those up, subtract this sum from the other direction, and if this value comes out negative, we multiply by a -1/2. If this value comes out positive, we multiply by the +1/2. The work for this one is down here in the corner, so when I do this times 1/2, I get a final area of exactly 30 units squared, which again is pretty interesting considering how jumbled up everything is here. We get a nice integer answer yet again for this problem. I'd encourage you to pause again. Sometimes the shoelace algorithm takes a second to figure out how you're setting it up and also to do the arithmetic for it. But here's my answer for this last one. The answer comes out to nice even 52 units squared. And if you're thinking that it always comes out to integers, that's almost true. It's always going to come out to something exact as an integer or something 0.5, as long as these are all integer values that you're given. So you're always going to end up with nice numbers. But be familiar with the shoelace algorithm because it is a big time saver for when you're trying to find the area on a graph.